Good morning, good evening, good afternoon. Today we're going to talk about OSPF version 2. We're going to go through the basics in this video, and then on a following video we'll go through some additional things. Today we're going to cover intra-area setup, inter-area setup. We're going to go through some basic show commands. We're going to also do the different types of authentication and show some debug commands. So you can see the topology here. We have area 0, area 5 and area 7. Between the routers we have it as following IP addresses. So each router has its own loopback, which is on 192.168.RR, the router number. So for example, on R5 right now we have 192.168.5.5. Then between the routers we have 192.168.RR.R. So the lowest router goes first. So 192.168.45.5. for example on R5 to R4. So we'll just open up all these ports and all the routers and then we'll begin. So what we'll start with is intra-area setup. So intra-area setup means that the two routers are within the same OSPF area. So what we'll do is we'll set up R4 and R5 for OSPF, and we'll carry out a capture between the two to see the different packet capture. So on R5 we'll go to capture and then 0/1. So you can see at the moment R4 is sending OSPF hellos to the broadcast address of OSPF, which is 224.0.0.5, as R4 is already set up on gig 0/1 for the network statement. So what we need to do is set up R5. So it's just as simple as enable config t router OSPF and then the process ID. But this is only locally significant. This does not affect any adjacencies with any neighbors. So what we'll do is we'll keep it consistent with all the routers. So we'll do 5 for OSPF 5 for R5. Then what we can do is set up the router ID. So router ID, and it's dotted decimal 32-bit, like so. If we don't set it up manually, automatically it will try to use the highest IP address on an active loopback and the highest active IP address on an interface if there's no loopback. So set up the router ID. Now we need to give it a network statement. So this doesn't advertise the network as such. It just activates OSPF on the interfaces that are within the network statement range. So for example, if I did network 0.0.0.0, a wildcard mask of 0.0.0.0, the reverse of this is 255.255.255.255. This would mean any interfaces that have an IP address is within router OSPF. Start sending hellos down that interface and send this information in the OSPF database. But what we'll do is be more specific and say 192.168.0.0.0.255.255, and we give it an area number area 5. So if we just do show IP interface brief, you can see with that network statement that this interface is in the network statement, and also this interface is within that network statement. Because if we do show IP OSPF interface brief, make it look tidier, you can see that those two interfaces now are members of the OSPF area. The black text was the OSPF messages that are being transferred between R4 and R5. To start with, they'll send hellos to each other on that broadcast addresses. Then you can see that a database descriptor is sent from 5 to 4. 4 will do the exact same to 5. That's telling them the contents of their database. For a router to be fully adjacent, they have to have identical databases. Once the databases have been described, then we go and ask for a request of any information that's within our neighbour's database that we get a copy of, which then the neighbour will then send a link state update, and then we would also be requested if anything within our database doesn't match on their neighbour, so they would request us for any information, then we would send that update. then we acknowledge that we've both received these updates. Once that's done, then we would go into a full adjacency. So the neighbor states are down, initiate, two-way, xstart, exchange, loading, and full. So initiate means that we're sending hellos. Two-way means that we've received a hello from a neighbor with our router ID inside. Then we go to xstart, which then is deciding who the master and the slave is between the two routers. Then we go into exchange. Exchange is where we send each other the database descriptors to tell each neighbor what we have within our database, which is show IP OSPF database. This is the contents on the router of the OSPF database, and we would send this to R4 to say what we have. Once we've done exchange, then we move on to loading. This is where we send requests and updates and acknowledgements. And once we've completed those 3 steps, then we have duplicate copies of the database, and then we go into full adjacency. And if we go back to show IP OSPF neighbor, you can see we've gone into a state of full. So just to show that process, what I can do, a good command to do is debug IP OSPF adjacency. Then let's do clear IP OSPF process. This is just us resetting the OSPF. Just do it now and debug all after all that commands. Let's go through that content. Then our interfaces have come back up. We've gone into a two-way communication, hence two-way, between R4 state two-way. Then we've gone into xstart and exchange. So we're preparing the database exchange. We're sending the database descriptor to R4. Received the database from R4 to 5. This is us in xstart. First database, and we are not the slave, so we're the master. Receiving database from 444. Exchange done. That's us done the database descriptors. Then we've gone into loading, which is sending link state requests, receiving link state updates. We've synchronized now with R4, and we've gone into a full adjacency. So with Intra area, we have within the database, if I show IP OSPF database, within the Intra area, so routers within the same area will send each other LSA type 1s and LSA type 2s. The router LSA, which is the LSA type 1, tells everybody within the OSPF area advertising routers and the links that are associated to that. So you can see from R5 we've advertised link count of 3. We just go into a more granular level, go 5.5.5. You can see that we have advertised the 192.168.5.5. We've also advertised the 192.168.45.5, and that is also a stub. So these are all sent by all the routers within the OSPF area. And then you have a type 2 LSA, which is a network state, which is a network LSA type 2, and this is advertised by the DR between the segment. So you can see the advertising router is 4.4.4.4. The network statement tells everybody within that segment who is talking really on that segment. For example, if we go back to the diagram, advertising router is 4.4.4. It will send out a network LSA, and it will say that the speakers on this segment is 5.5.5.5, and that is all, because there's nobody else within that network segment between 4 and 5. And also if we go to R2, you should see the exact same LSA type 1s. So this is for area 0, we need to go to area 5. So you can see that the R4 is the DR for this segment. Use the advertising router. So DRs are the only ones that send net link states, so network LSAs. And then again you have all the router LSAs for that segment. So when I mentioned DR is a designated router. So these are the routers who are in charge of the network segment, and then you have a BDR, a backup designated router, and a DR other. So if you have multiple routers within the same segment, you would nominate a DR, which is done by the higher priority. If a tie, then the highest router ID. Once the DR has been nominated, then the second highest priority or router ID would become the BDR, and everybody else in that network segment become a DR other. I'll just put up a diagram just to demonstrate the DR, BDR, and the DR other relationships between each other. So DR others would only form a full adjacency with a DR and a BDR, and they would not form adjacency with any of the other DR others. This is to produce less traffic of OSPF. DR and the BDR process only happens on two different types of networks, so a broadcast and a non-broadcast. So we talked about the different OSPF network types. So you have broadcast, non-broadcast, point-to-point, point-to-multipoint, and point-to-multipoint non-broadcast. With the broadcast, the timers are 10 seconds, then 40 seconds for the dead interval, and on the wait time of 40 seconds. A non-broadcast, we're talking 30 seconds, 120 seconds, and again 120 seconds. And the point-to-point is the same as broadcast, that's 10 seconds, 40 seconds, 40 seconds, and the point-to-multipoint and the point-to-multipoint non-broadcast are 30 seconds, 120 seconds, and 120 seconds. You can change these timers, but these are just the recommendations for the specific network type. So we've done the intra area. So if we just have a look at the routes on R5 again, what I want to cover next is the OSPF cost. So we've done a show IP routes. We can see the OIA is inter area, and then just the O is the intra area. So you can see we have an administrative distance of 110 for OSPF, and you can see that we have a cost of 2. So the way this is carried out is when the OSPF network is being advertised through the segments of the network, each router finds out its cost to get to that destination by taking what is called the reference bandwidth and dividing it against their bandwidth. So if you do a show IP protocols, OSPF, I think it is, you can see that the reference bandwidth is 100 megabytes per second. So the problem we've got with just having it with the defaults is if we use anything above fast Ethernet, OSPF cannot define the differences between gig and anything above. So what we need to do is change the reference bandwidth to a higher value. So the way we do that is config T router OSPF 5, and then it's auto cost reference bandwidth, and then we'll just put 1000, and I'll just duplicate that on the rest of the routers. Now we've changed the reference bandwidth and all the routers within the OSPF domain. Any difference between fast Ethernet and gig interfaces, OSPF will be able to define a different cost for each when it does the reference bandwidth divided by the actual bandwidth. So we'll move on to inter-area of OSPF. So the difference with this is when OSPF databases are advertised to a different area number. So if we go back to the diagram, I'll just go through some detail here. So we've used mostly area 5 for this demonstration. So for area 0, this is very important in OSPF. This is called the backbone. So for example, if we had a link between R5 and R7, and R5 tried to advertise all of its links within area 5 to area 7, this would not work. This is an OSPF rule that inter-area routes must go through the backbone to then be advertised to a different area. So area 5 would have to advertise its routes to the area 0 backbone, and then area 0 would then advertise its routes to area 7. There is ways to get around this. So for example, if we had from R7 to R8, 9 and had a different area number there, we can use virtual links or GREs to resolve that issue to get a connection back to area 0. But to allow us to advertise into a different area, we have to go to the backbone. So how this works is you have type 1 and type 2 LSAs as spoken about earlier on. So what R2 and R3 are classed as, because you can see they have connections in 2 different areas, they are now classed as area border routers. So that means that it takes the routes from area 5 to area 0, or area 0 to area 7, and vice versa. So what R2 will do, it will receive the type 1 LSAs from all its routers within area 5, and then it will advertise those areas into area 0 as a type 3 LSA. What we'll do is we'll open up R1 and we'll show an example of that. So if we do show IP OSPF database, you can see here the summary network LSA. These are the type 3 LSAs that we have within area 0. So you can see the link IDs of 4.4, 5.5, 6.6, 7.7. These are all the routers that are in different areas from area 0. And the advertising routers is either the router ID of R2 or R3, because these are the ABRs between these different areas. So this is inter-area routing. So as I mentioned earlier when we did the show IP route OSPF, the IAs are the ones that have come from a different area. The other ones that we can mention here is E1s, E2, N1 and N2. So the E1s and the E2s are when they are redistributed from another means into OSPF. So an E2 is an OSPF external type 2. So that means that the metric that is set for that route when it comes into OSPF, as it travels across the rest of the OSPF areas, the metric will remain fixed. If it's an E1 OSPF, then it means when it travels through the OSPF, so it's redistributed into OSPF, and as it travels OSPF, its metric will increase as the same for the rest of the OSPF network. And then an N1 and an N2 is for an NSSS-A external. So this is when we use type 7 LSAs. I don't want to go into this too much. This is something I'm going to cover in another video. But I just want to show you the codes here. So as we covered intra, inter, what I want to finally cover is the basics of authentication. So what I'll do is I'll set up between R5 and R4 authentication, and R6 and R7 a different type of authentication. So you have with OSPF version 2, you have 3 different versions. You have type 0, which is no authentication. So for example, the diagram we have right now and the setup we have no authentication. So that means somebody could plug in an OSPF router, send out hellos to R5, and then he would become a part of that OSPF domain, and then he could inject false routes into our OSPF domain. Then you have type 1, which is plain text, so the password is sent in the OSPF hellos but are unencrypted. So someone could still, if they had a packet sniffer, capture your OSPF hellos and still be able to see the password to then join. And then the last one is type 2, which is message digest, which uses an MD5 hashing to encrypt the password as it's sent in the hello packets. One way to, as I mentioned about the no authentication, and one way to minimize the possibilities is to have passive interfaces. So what you could do is set up an interface as a passive interface, which means that OSPF will not send hellos down that network. So as simple as config t router OSPF1, and then it's just passive interface, the interface name that you want to give. So back to authentication. Between R4 and R5, we're going to set up authentication. This could be done 2 separate ways. It could be done on the interface, or it can also be done as an area. So config t router OSPF. Sorry, we'll do R5 on the area. So we'll do interface gig 0/1 IP OSPF authentication, and then authentication key. We're going to give it Cisco 1, 2, 3. Okay, so that's that area done. Then we'll go to R5, and then we can go enable config t router OSPF 5. Did I do that on the right area? Just double check. Yeah, we did it on the interface, that's fine. And then area 5, authentication. Area 5, authentication. So that's just enabled the authentication on the area, but you still have to do the password on the interfaces. So interface gig 0/1, IP OSPF authentication key, and then Cisco 1, 2, 3. So we had the capture set up previously. Let's see if we can capture it now. If we open up the OSPF, you can already see it. So the authentication data is simple, Cisco 1, 2, 3. So you can see somebody who has a packet capture between your routers could capture your password, enter that into their configuration, and they can still send hellos into your OSPF domain and form adjacent. And what we'll do is between R6 and R7, we will do message digest. So config T, interface gig 0/0, IP OSPF authentication. Message digest, IP OSPF message digest, key number, MD5, and then Cisco 1, 2, 3. Key already exists, we'll just change that. So that's us set up R6. We'll quickly just set up a capture. So hellos come from 7. We should see the adjacency drop, so you can see the authentication data there. So now we've done R6, let's move to R7. Enable config T, router OSPF 7, and then it's IP OSPF, no sorry, it's area 7, authentication message digest. And again, these passwords still need to be done on the interface. So interface gig 0/0, IP OSPF message digest key, Cisco 1, 2, 3. Forgot to put MD5 there. So obviously the hello is still seeable, so it's not, none of it's encrypted, so you can still read it. You can see that the passwords now are all encrypted, so I cannot intercept that. So that's from R6, that's from R7. So what I would like to do is just go through some of the show commands. So show IP OSPF interface, and these will give you detailed information. So you can see network type broadcast, network type loopback. Just seeing that there, loopback. One thing to note is when you're advertising a loopback into OSPF, IP address larger than a /32, OSPF will automatically advertise it as a /32. So if you did a /24, OSPF would automatically change it to a /32 when it's advertised. And on top of that one, it's brief, so much shorter summary. Then show IP OSPF database. There's a detailed about all the different types within OSPF version 2. And they're kind of some of the basic commands that you can use just to get OSPF and have a look at what it's actually doing. Then the other ones is debug IP OSPF hello. And the other one is debug, as I used previously, debug IP OSPF adjacency. These are very useful if you can try and figure out why the adjacency is not forming between two routers. And just on that debug as well, between two routers to form adjacency, you need to take into consideration that 1, you have connectivity between the two routers, you have the same area, IP address and subnet mask on the interface, MTU, timers, network type, they both need to be in the same network type. So if you had broadcast and point-to-point, broadcast obviously you have the DR election, but point-to-point we do not. Unique router IDs, so they have to have unique router IDs within the OSPF domain. But this is just the basics of OSPF we've covered today. So I hope you've enjoyed. Leave a like and subscribe, and we'll see you next week for another video. Thank you.